Warwick University. Let's talk about the Allen-Cahn stochastic.
Okay. Yeah, thank you very much. Thanks for the introduction, and thanks for having me here, and also thanks to you all for sticking with me until the very end. So what I want to present today is a kind of a work with a joint work with Felix Otto and Maria Westickenberg. That's a project that has been going on for quite a while, and it's concerned with invariant measure of the stochastic Allen-Cahn equation. So let me just jump right in. So the stochastic Allen-Cahn equation for me is always going to mean this. So we look at this very simple reaction diffusion equation. We have time derivative here. We have a Laplacian, but we're in one space dimension, so just write it as the second derivative. We have this very special nonlinearity. So we have the derivative of this double well potential function, and v throughout the talk is always going to denote exactly this double well. So you could think of the standard quartic u squared minus 1 squared, but it can be anything else. What is going to be very important in the sequel is actually the assumption that v is symmetric. So we're always going to assume that. And as usual, w dot is going to denote space-time white noise. So from an existence and uniqueness point of view, of course, you all know that this equation is well posed. There's no problem at all to make sense of this. And just to get started, let me perhaps remind you all very briefly what the dynamics of this equation look like. So if you think of our one-dimensional space, here's minus L and L. And throughout the talk, you should really think of L as being rather large. And we have here our local minima. Here's minus 1. Here's plus 1. And I just, for simplicity, I will always assume that the minima of the potential are exactly at plus minus 1, but that's, of course, just convention. It doesn't really matter. Then this nonlinearity, the v prime term there, will account for the solution to locally always be close to these plus 1 or minus 1 faces. So what this typical solution will look like after a while is always a profile like that. For example, with 3 such transitions. And now epsilon, the noise, should be thought of as very small. So you have these small fluctuations around such a profile. So, and the typical fluctuations will be of square root of epsilon, as the square root of epsilon in front of the noise indicates. And the scaling of the solution, the way I have written it down there, is such that a typical interface here will be of order 1. Okay? Now, the questions. So as I said, where did I put my pointer? Here. As I said, now this equation, the way I have written it down, has a couple of parameters. The parameters relevant for this talk will be the small noise strength, epsilon. We should have think of this as being very small. Order 1, as I said here, is the typical length of the interface, and the system size will be very large in our throughout the talk. Okay. And what I'm interested in this setting are the following two kind of meta questions. Is the first thing actually concerns very large L. So the question is, do we see nucleation? Which is the question, does it happen that the noise at some point in the system is so strong that it actually creates such a new transition here? Okay. Of course, this is on a given interval. This is extremely unlikely. But if our system L is actually very large, this may well happen. The other question concerns the effect of the boundary conditions on the system behavior. But this is actually more a question about small l. So the question is, how quickly does the system actually forget if I put some conditions on the boundary, if I fix it? So actually, I can be more specific throughout for most of the talk. I'm actually always going to assume that I attach the solution to minus 1 here, and I attach the solution to plus 1 over here, and then I'm going to see what is the influence of this assumption on the system. Okay. Now, I actually cheated a slight bit. I'm not actually going to look at the dynamic equation. I'm only going to look at the invariant measure for this. So from now on, this was actually the only SPDE I'm going to show in this talk. And actually, the whole talk makes complete sense without SPDE. So as I said here, I will always put Dirichlet boundary conditions on my equation. And as I also said, they will actually typically be minus 1 here and plus 1 to the right. But let's, for the moment, be more less specific. Then the invariant measure, so the equilibrium state of the system, can be described very explicitly in the following way. So you have this auxiliary measure here. You start with that, and that is just, so I have denoted this with this curly W with lots of decoration. So here you have the left boundary point, so the left directly boundary condition, the right directly boundary condition, the noise strength, and the system size. And throughout the talk, I will not be consistent in putting all the decoration there, but I leave it for most of the time. So this is just a Brownian bridge on this interval. So it's just a Brownian bridge connecting over this large interval minus L to L, these boundary points minus 1 and U minus and U plus. And then that's, of course, I mean, as you know, this is actually the invariant measure for the linear equation. So if you didn't have the potential term, this would already be the invariant measure. And the effect of the nonlinearity is just such a density. So the invariant measure mu that we will actually be concerned with is absolutely continuous with respect to this curly W measure. And the density is given by such an explicit Feynman-Katz type term. So what it means is just that this potential energy kind of is rather large if the system spends a lot of time away from -1 or +1. And so this punishes that, and a typical path may look like that, for example. Although this is not actually a sample, this is a complete cheat. Okay, so far so good. So now the questions that I posed on the previous slide can actually also be asked for this invariant measure. And now the meta question here is, how does the behavior of this profile U that is distributed according to the measure mu depend on the small parameter epsilon and the large parameter L? Okay. Good. So, I mean, of course, this is. I'm sorry for boring you if you know all of these things, but of course, this measure has a natural Gibbs structure. So the energy for the Allen-Cahn is a gradient flow, as I will show you in 2 points. And the energy is so you have this Gaussian kind of energy, and this nonlinear energy is of course very important for this problem. And formally, we have this Gibbs measure type structure. So of course, this doesn't really make sense because the energy for a Brownian path is actually almost surely infinite. But this formula gives you lots of the right intuition about this measure, and just kind of to see why this formula is already useful in guessing the right behavior. If you just formally write that the Allen-Cahn equation that I wrote on the first slide is actually the L2 gradient flow of this energy, and here's the noise term, then already you can guess that this should be the invariant measure. At least in finite dimensions, that's true, right? If you have a gradient, gradient diffusion, dx is gradient of f plus noise, then this measure is going to be the invariant measure, and it turns out to also be true in the infinite dimensional case. And this is not even so much of a cheat because this is really how you prove that. Okay, so it's I think this is a fair proof actually of this. Good. So let me also remind you of the most important facts of this energy functional, which will be crucial later, which will be important later on. So if you just look at this functional on the whole line now, but our L is going to be rather large, so it seems fair to look at large intervals, and you ask yourself how much energy does it cost to go from -1 to +1. So what's the minimum energy of any path that connects -1 at -infinity to +1 and +infinity? Then there's this very classical trick from the calculus of variation based on a paper by Murico and Mortola in the 70s, where you actually just complete the square. So you write this, you have this, you write this, you put the 2 in front, then you put a 2 here, square root and the square, so that's just that term. And then you complete the square, and in order to get an identity, you just get this extra term here. And so I've done nothing, but then this term is actually non-negative. So if I want to just get a bound, I can drop it. And this is a total derivative, so I can use chain rule and get something that only depends on the boundary conditions, right? This is, I think this is one of the most popular tricks in calculus of variation. And this constant C0 is going to be very important throughout the talk. So this is just the energetic cost for one transition. Okay. And actually, this formula also tells me what the optimal profiles look like, because the optimal profiles are just those profiles that actually for which this term is actually 0, and that's an ODE which one can solve explicitly, and you get these actually in the standard case of u² minus 1 squared. This is just the hyperbolic tangent, but in general they always look like that. They decay exponentially here to +1, exponentially here to -1, and of course the whole problem is translation invariant. So you have a whole one parameter family of minimizers, and you can just shift it around, and you have all your minimizers. Okay. So far, so good. So now let's go back to the measure, and let's look back at the question that we wanted to address. So actually the problem in the case where L, now I have denoted that with these twiddly equal 1, this just means that L is actually bounded. Then the problem is extremely simple and has been solved in the 70s, I guess. Because in this case you have a large deviation principle, and it's actually very easy to prove. You have a large deviation for the underlying Gaussian measure, and then the Bajadans lemma, really a straightforward application of Bajadans lemma, gives you that you have that your measures for fixed system size L satisfy a large deviation principle, and the rate function is just given by the energy. So more specifically, in this context, that means if I fix, for example, these two boundary conditions, then I have a concentration around the minimizers of the energy. So in this particular case, the profile would look something like that. And all this large deviation principle also tells me that if I want to look at the probability of having transitions, so for example, I could have a path that looks like that. I do such a transition. Then I also know that, I mean, this essentially here I just have some energy at the boundary. Here I have also some energy at the boundary, and in between here in the bulk I have essentially no energy. And here, okay, here in this bit of the bulk I also have no energy. Here I have no energy. Here I have the same boundary energy, and the difference is just given by 2 times C naught essentially. So the probability of seeing such 2 transitions with these boundary conditions is just essentially given by that. That's what large deviation tells me, right? So that C naught is the cost of one transition, and I pay that with 1 over epsilon, so it's extremely unlikely. Now, so the thing is, so now we want to look at larger L, and so the system, the whole problem is then extremely reminiscent of the classical problem in large deviation theory of exiting from a diffusion process from a domain. Okay. So for those of you who do not know that, let me just very briefly recall without putting anything on the screen. What the problem is, you look at the diffusion process, so you have a drift, also perhaps in a double well potential, but there may be a much more evolved situation with an additive noise, may also be not additive. And then you have a similar large deviation principle that tells you that in a given interval, going from one well to the other one is exponentially unlikely. And so that you can just use, if you use the Markov property, which is really crucial in this business, then you just try again and again and again and again. And every try is independent of the previous try because of the Markov property. And then that tells you that it takes you exponentially long to actually go over there. Okay? So we want to do something similar, and the heuristic here are extremely simple. So you would just cut our large system. So I have now put these boundary conditions -1 and +1 here. I cut my large system L into n, but that's the same as L boxes of size order 1. Okay? So that's that I've indicated here with all these cuts. And then I would think that the probability of seeing a transition in this box, and in this box, and in this box, and in this box, and in every single box I should just pay the energetic price. So the probability of seeing exactly this kind of configuration should just be e to the minus c over epsilon, and I have 1, 2, 3, 4 transitions. The 5th one doesn't count because it comes from the boundary condition. So I would expect to have e to the minus 4 c naught over epsilon, right? But now, of course, I have lots of boxes, and I can sum over all of them. The events are essentially disjoint. So that gives me this scaling factor here. The number of boxes that I have scales essentially like L to the 2n. And as before, the one kind of the rightmost transition doesn't count because it's enforced from the boundary condition. So it doesn't count either for the energy, but it also doesn't give me anything in terms of the entropy. Okay, so this heuristic is very easy, and it turns out, okay, we can prove that. That's the first result that I want to present. So let me be a bit more specific about what I mean by a transition layer. A transition layer is really exactly what you would think it is. So I define a transition layer on a given subinterval. If at the boundary value it's exactly -1 and +1 at the right, so I just swap go over once exactly, and I'm precisely I'm exactly, so my absolute value is just exactly smaller than 1 in between. And then so as I said before, we impose these boundary conditions, -1 at the left and +1 to the right. And now the assumption on our system size is that we are exactly subcritical here. So let me remind you that the C naught is just the energetic cost of a transition. And now we allow our system to grow exponentially. but we don't allow it to grow exponentially at the same scale. So the exponential growth rate must be strictly smaller than the energetic cost for a transition. Okay, and then this is actually true on a large deviation scale. So the probability of 2n plus 1 transition, exactly the heuristics that I told you. You pick up this entropic factor L to the 2n in front, and you get this x to the minus. Here's the energetic cost. And as usual in large deviation theory, you have the error already in the exponent. So this bound should be read for any gamma there exists an epsilon naught, such that for every epsilon this is true with upper and lower bounds. Okay. And actually, this result does not depend very strongly on the boundary conditions. So we could do the same thing also for say periodic boundary conditions. But then of course the scaling would be slightly different. So for periodic boundary conditions, we would have 2n transition scales exactly like that, or we could also have we could even put homogeneous Dirichlet boundary conditions. So then we could even have an odd number of transitions, and then the scaling would just always be the one that you guess. Okay.
So how big has L to be in order to see that the periodic boundary conditions do not give you the periodic solution?
What do you mean by the periodic solution?
Well, I mean, if I fix my my boundary data to a different Dirichlet datum, then I get the periodic solution instead of the one which is with the exponential tail, right?
I mean, our this assumption, our L is always going to be very large, so we are always going to have diverging L. But my next slide actually goes in that direction. So let me perhaps show you my next slide. Okay. But I mean, for this effect, the boundary conditions don't really matter. I could even put 1, and then this is just if I put 1 here, then this prefactor drops. It doesn't really matter then, and then it's just a large deviation statement.
Right, but since you have the explicit dependence on L, I was wondering.
But this is only on exponential scale.
Okay.
I mean, I have an exponential error already here, and if L grows sub-exponentially, it completely vanishes from the bound. So this is really only relevant for very large L. But so but the question about the effect of the boundary condition is I hope is answered on this slide. So we still have this bound on the upper bound on the system is in the system size. And if you recall the previous slide, then this is exactly the scale. So this just tells me that the probability of having more than one jump goes to 0, and it goes to 0 exponentially quickly. And then if in addition we make this very mild lower growth assumption on the system size, so I mean, of course, there's a huge amount of space between logarithmic growth and exponential growth here. Then our jump will be uniformly distributed over the system. And we have a very precise way of saying that it will be uniformly distributed over the system. So not just we rescale everything to a box of order 1 and we get uniform distribution, but we have this much more refined information. We look at sub-windows of our interval of length at least large with respect to the logarithm of epsilon. So these are the scales on which we can measure our uniform distribution. And then the statement looks like that. So this is the probability of having, oh, that should be a j, sorry. So that's so having the probability of having a transition in this interval jx. So if we have uniform distribution, it should really scale like d over L, right? So the system, or this thing has Lebesgue measure 2d, and the whole system has length 2L. So this is just so this should be approximately 1. And now if you subtract 1 and take the supremum over x, this converges to 0, and we have pretty precise control on the error terms. Okay, so this means we don't only know that we have uniform distribution, but we actually also know it down, up, down, all the way up to logarithmic scales. Okay, good. So that's actually all the results I want to give you, but let me perhaps discuss them a bit. So in particular, let me start with discussing the distribution result. So there's a very nice paper by these 3 authors from 2008. And actually, there was a talk in the I think Stella Prasesco gave a talk about exactly this work in the first instance of this meeting, so the 2010 version of this meeting, where she presented exactly that. So they look exactly at the same system, with a very specific choice of scaling of L. L is exactly logarithmic. Then my conclusion with the uniform distribution is wrong. And what happens for them is, if they look in this scaling, then actually their measures are tight. So in particular, the distribution of the jump does not go off to infinity, but it's concentrated, and it's concentrated in a very strong way. So they have a weak convergence of the distribution of the jump, and in the limit they have this doubly exponential decay. So it's kind of it has very small tails. So you have an x to the minus cosh here, and they could describe that in this case. So this shows that our lower bound on the log is clearly sharp.
So psi is the position of the jump.
Yes, psi is the jump position.
And it has to be exactly 1/4.
Yes, but the quarter, of course, depends on the specific choice of V. So this is true for the standard quartic double well. But I think they didn't have a general formula for the general case. But yeah. But what they conjecture, actually they conjecture, they don't prove, but they say that if you put a prefactor here which is strictly smaller than a quarter, then you get in the limit you Dirac at 0. And in the case where you get something actually a bit bigger than a quarter, then it will wander off to infinity. But that they didn't specify. And of course, our result is in a way is a bit weaker because we actually assume that the quotient goes to 0, so we don't capture that in that precisely. Let me also mention something I did before. This was essentially something this was something I did in my PhD. So I also looked at the same system a bit bigger than here, but much smaller than we did, and then I could also show that we have concentration near the energy minimizers. Right, but this is of course much weaker than what we have. Let me perhaps also mention a bit about how to go about how these people went about proving things. So there's of course a couple of explicit representation for these measures and methods to work with this. And what they did is this measure can actually be written as a conditioned diffusion process. So this, it makes sense. You have this Feynman-Katz term, and the Feynman-Katz term can actually be translated into a drift for the SDE. And this drift is this A epsilon. But there's actually not an explicit formula for the A epsilon, but it's kind of semi-implicit. So it's the logarithmic derivative of the ground state of the associated of the Schrödinger operator associated to the problem. And so they were calculating with this formula, and so we really didn't want to do that because working with these conditioned diffusion, this logarithmic term in the drift at the right-hand side is really a bit of a pain to do calculations with. And also they had to work rather hard to do that, and this is something we really didn't want. Let me also mention a bit what I did before. The approach was also very different from what I'm going to explain to you in a minute. So I looked at discretizations of the measure where actually this Gibbs formula is rigorous and true. And then this was really derived just with explicit bounds on the energy landscape. So you really calculate so you actually develop the energy near the minimizers, and then do a Gaussian approximation, and then do a pass to the limit in all your bounds and see that things are compatible. But these error terms, they actually become much too large as soon as your system is large. And this is, as you can see, quite far away from the critical scale. So this just suggests that this approach is not very good, actually. Okay, so now let me tell you how we do it. So, before I tell you how we do it, let me tell you what are the ingredients to do in it. So I told you this thing is very related to Freitlin-Wenzel and this idea of patching, and then things should be independent. And of course, our measure has a version of the Markov property as well. It would also be a Markov process in time, but then it would be Markov in the usual way, but then it would be inhomogeneous, and that we don't like because we have the effect of the right boundary condition. But we have a kind of two-sided homogeneous Markov property, which just tells us, so even a strong version of the homogeneous property. So these chi minus and chi plus are now left and right stopping times, and you define stopping times the way you points, and you define left and right stopping points the way everybody would define left and right stopping points. And then exactly the kind of Markov property that you would guess. So you take the conditional expectation, and here in my measure mu, I have dropped all the decoration, of course. So you take the conditional expectation and condition on the sigma fields generated from everything to the left of the stopping point and everything to the right of the stopping point. and then you get exactly, so you can of course observe your process. That's what this symbol is supposed to mean. You can observe your process up to the stopping times chi minus and plus, and then in between it's independent from, well, it's just distributed according to the measure. So you just resample everything in the middle according to the same measure. So it's completely homogeneous and nice. Okay, perhaps this formula is not very intuitive. So the Markov property is the one you would guess it is. Okay. The second ingredient is, as I might already suggest, what did already suggest, are these large deviation bounds, and it's of course true these large deviation bounds, the way I stated them on the couple of slides ago, are of course completely classical. It's just kind of a version of Bachadan's lemma, if you want. And so what we needed here is a slightly more uniform version of this. So we need this. This is just the bound that you would get from Bachadan's lemma. So that just means that for nice functions, the probability of seeing a path in that given set of function is given on exponential scale. Here's 1 over epsilon by the energy difference. So you have the here you have the energy of so as you usually do in large deviation, the infimum of the energy over that set, and then you have to subtract the infimum given the boundary conditions. Let me perhaps stress that this large deviation principle only holds if we already condition on the boundary conditions. So this is not, as in other continuum system, a large deviation principle that just tells us that the probability of seeing a given path is just given by the energy, but we really have to condition on the boundary conditions. Otherwise, it's not true in our case. And in the fact that it cannot be true in general, you can just see it by. Otherwise, this would immediately imply that the probability of seeing a transition is 0, and this is clearly not true because by our boundary conditions it's 1. Okay. Let me also point out that, okay, I mean, it's not kind of very interesting, but it takes a couple of pages to do. We actually need these bounds uniform in everything. So we need them to be uniform in the boundary data, uniform in the system size, at least locally uniform in the system size. We need them even locally in the sets and locally in the energy functionals. And it's in a way not a very interesting exercise because it's exactly the classical strategy. You just have to go through everything and see what depends on what, and it takes a couple of pages, but it's not very enlightening anyway, so it's true. Okay. Okay, so this aside, now let me tell you what's the interesting bit. So Freitin-Wenzel actually does not work directly. You have to be a bit tricky about it. So what would Freitin-Wenzel, what would you do? So you look at you want to calculate the probability. You have put your boxes as I had before, and you want to calculate the probability of seeing, say, a transition in this box, a transition in this box, and the transition in this box, and all these boxes. But let me perhaps focus for the moment only on this box. So what would you do? The naive thing, you would just, so this is the probability of seeing a transition in this interval. You condition on the boundary values here, or you condition on boundary values, say, a bit 1 box to the left or 1 box to the right, but somewhere near this interval. So this is just what this integral means. So this is just the 2-dimensional marginal of your field U at these 2 points. This you can integrate out. Then even the weak version, so the standard version of the Markov property tells me that here I have the measure. Now I have as decoration put my boundary values that I have integrated out here. And here I have the transition, the probability of seeing a transition in this interval given these boundary delta, right? That's what Markov property tells me. And now I would like to say, well, large deviation tells me that this is small. Now it turns out that's actually it's just not true. And just if you think about it, this is just a kind of simple geometric question. If you think about it, here I already know my typical boundary data on my set are going to be up here, and another boundary data will be down here. Okay? Given these boundary data, the probability of seeing a transition is 1. Right? Because the boundary data already implies that we will see a transition on this interval. On the other hand, yeah, so what this just means is that all the information about the location of the transitions, and if we have several, is really covered in these 2-dimensional marginals that we don't have any handle on at all. We have perfect control on these local, the local behavior of the field given the boundary conditions, but this doesn't help us at all. Okay, so that's the problem. As I say here, all the information about the macroscopic shape of these profiles is really covered in these 2-point function, or I could of course also do this. I will later on do this with higher dimensional marginals. But so the problem that we encounter here is really how to translate the local information that we have from the large deviation principle into global information about the field. Okay. Now the trick how we do this is, as I suggest here, symmetry helps, and we need to really we need to do a trick. So the idea is we transform the event about which we don't know anything into an event about which we know everything. Okay, so that's the hope. So we don't know how to calculate the probability of seeing the transitions where we want, but we can perhaps find a transformation of path space that transforms our path into other paths, and that do something that we can show that it doesn't happen. And this is quite easy in this case, actually. So what you do is we just take these hitting points here of 0 and here we have more hitting points of 0, and we take them to be, say, the leftmost in that interval and the rightmost in that interval and the leftmost in that interval and these intervals. And then we recall that we have the strong version of the Markov property, of this Markov field property. And this tells me in particular that the distribution of the thing between these two stopping points is distributed according to the same measure that I had before, independent of everything at the outside. But that's good, because our measure is actually invariant under reflection. So that means this reflection operator R, if we define it that way, actually preserves our measure mu. Okay? And hence, we can reduce the problem of calculating the probability or bounding the probability of seeing many transitions. We can reduce that to the problem of seeing these funny bumps here. So these reflected paths will always have an excursion from -1 to 0 and back to -1, and in this interval as well from -1 to 0 and back. So this is just what I have here. So this reflection operator transition intervals I is the same as the probability of seeing these wasted excursions, as we call them. So wasted excursions are exactly those things from -1 to 0 and back. And now we can do exactly the same trick as I wanted on the previous slide. So we condition on all these values here. And then this is always unlikely locally, because independent of the boundary data, this will never happen. And we have very good control on the energetic cost of that. And this is actually very easy to bound with just large deviation and some really easy control of the energy function, just tricks very similar to this Modica modular trick that I showed you. Let me also point out that here it's really important that you have these uniform bounds on the large deviation, because we actually want to integrate out the boundary value, and hence we have to know that we are able to choose the same epsilon naught such that the bound holds. So we actually had to go through the exercise of reproving all these things. Okay. Okay, that's perhaps not the more interesting part. Let me perhaps spend a bit more time. So that's all I want to say actually about my first theorem. Let me perhaps spend a bit more time on the uniform distribution, because that may be more interesting. So in the uniform distribution, we have a similar. So the spirit of the argument is in a way very similar. We fix ourselves some large interval jy, and of course this jy should later on, we should think of these at least to be logarithmically large, but for the moment it doesn't matter. And we fix another interval of the same length. And what our uniform distribution essentially says, that is the probability of having a transition here is the same as the probability of having a transition there, right? That's what we want to prove in the end of the day. Okay. So let's just find another transformation that does that for us, okay? So what we do is we fix ourselves some auxiliary intervals jy minus here and jz plus to the right of these. And let's hope that we have hitting points of -1 here, down here, and a hitting point of +1 up here, exact hitting points. And we will, as soon as they exist, we can also take the right and leftmost here and the rightmost here. And then again, we use the strong Markov property that tells us if I just reflect my path in between, so I do a point reflection around the middle, then this will again preserve my measure. And this point reflection is very nice, because this point reflection has now actually moved my transition in this interval jy into the interval jz. Well, okay, the stopping points are not exactly the same distance, so it has just moved it close to jz, but good enough for the moment. Okay, so this looks very easy. So a bit of the work essentially lies in showing that these stopping times actually exist, and how big we have to choose these intervals jy minus here and jz plus to the right. So that is done in so this is the key lemma for that. So let me just put some notation. So this is just the set of functions that we are interested in. So that's just the profiles u that have these delta up layers. I haven't actually said what delta up layers are. So we actually never work with these transitions, but we actually only work from transitions from -1 plus delta to +1 minus delta, and that's exactly what these delta minus up layers are. And so this is just the set of paths that we are interested, that we start with. And let me recall that the aim of this argument is to show that the probability for this set is the same as the probability for the set where I have replaced the j here with a z, right? So that's the aim. And we have some extra technical conditions for the path to not do crazy things, but let's drop that. And now the key lemma is the following. So we fix our auxiliary intervals to the left and to the right to have exactly this size. So there should be log epsilon. That's where the log epsilon comes from. And then we've also fixed a large constant k bar. But k bar will later also grow in epsilon, but only very, very slowly. And then we have this bound, the probability. So now I have put back all the decoration, but it's always the same u. The probability of the set of paths that are in this nice set that we're interested in. So the paths that do a transition in that interval, and that do not have a hitting point of -1 in this interval at the left. This is very small times the probability of the path. So this is really a statement about conditional probabilities, right? So I didn't write it that way, but it's really a statement about conditional probabilities, and we need it to be a statement about conditional probabilities. Now, what is this error term? This error term consists of 3 terms. And of course, I haven't actually even defined all the terms here, but let me just tell you that this is the probability that we have actually another extra transition to the left. So that's with a slightly different scaling, but that's the term that you would have. This is another term that tells you, so this is the probability of being further than delta away, say being further than a half away on that interval from -1. And this is the probability of not actually hitting 0. And I want to explain this part of the bound on the next slide, actually. Let me just, before I do that, tell you that, of course, the same bound is actually also true for the right interval. So that's but symmetry and not very difficult. So I will only explain this part. So let me come to this term. So, and that's also the same k bar as we have here. So these terms have already taken care of. These have already told me that I know that I'm at least close to a half in that interval, to -1 or +1. Okay. So how do I conclude from there? And that's the key lemma that makes all of this work. So that's the lemma close to 1 is the key lemma for the proof of the hitting lemma. So we fix small epsilon naught, but small but order 1, and epsilon is of course smaller than this epsilon naught. And then we fix our k epsilon now. This is an interval. So the interval will exactly scale logarithmically in epsilon. So this epsilon naught, you should think of this as a small but order 1 constant, and this epsilon will be very small. So this L naught is just an order 1 quantity that we choose in a convenient way. So these intervals will really scale exactly logarithmically. Then the statement is the probability of being further away than epsilon over epsilon naught. So recall, this is small but order 1 constant, and this is really the right scaling. So I told you on this picture already that the small fluctuations here are of order square root of epsilon, and this is exactly the same square root of epsilon that you see up here. So the probability of being in the middle of the interval, okay, so this is a large interval to the outside, and now I only look at the middle of the interval. Probability of on the middle of the interval to be further away than that, conditioned, so this is the condition that we already know that we're not further than a half. Okay, so this is where we put all the knowledge that we had from the extra terms. So we know already that we're not further than a half, so we put that into this. So then this here will be small in this sense. So we have here a minus, so this is order 1, right? So this doesn't scale in epsilon anymore, but it can't because we're already on the right scale for epsilon. But we can still make this order 1 constant as small as we want by choosing epsilon small enough. Okay, so that's very convenient. And this is essentially, so this small constant here is essentially the same as the lambda here. Okay, so this is the lemma. This is the kind of the key lemma that makes this work. And let me give you a kind of picture proof of this lemma. So we already know this is my large interval, right? So this is L epsilon, and I have put L epsilon into all these small boxes here. So these are all small boxes of length L naught, and L naught is an order 1 quantity. So I have all these logarithmic in epsilon many small boxes. And here I've already drawn the line. So this is the line +1, and this is the line 1/2. So I already know from all the a priori information that I will always be above this line 1/2. Okay. So now I apply large deviation just on this interval and this boundary point, which I haven't put here. Okay. And this tells me I already know here I'm smaller than 1/2. Here I'm smaller than 1/2. Then with probability 1 minus exponentially small, I will be actually smaller than 1/4 in the middle here. Right? That's what the large deviation tells me. And I can do that because I know that I'm bigger than 1/2 on the whole interval. I can do this for every single small subinterval here, and I just sum over these bounds, and then I get the probability. This A is just the condition that I already have, so I already know I'm smaller than 1/2. So if I know that on the slightly bigger interval I'm smaller than 1/2, so this big interval, then I already know that on this slightly smaller interval here, I will also, with very high probability, be closer than 1/4. So the probability that I'm bigger than 1/4 scales like this large deviation thing here, and I have a k in front, which is just the sum over all the intervals. Okay. So far, so good. Now I do the same again. So now I look at this set here, and I rescale my process on this set. So I just blow it up around -1 by a factor of 2. Okay. Then my new measure, so my blown up U hat here, is also still distributed according to Gibbs measure, but the energy slightly changes. So the kinetic term will be the same. My potential rescales in this way, and the temperature scales with a factor of 4. Okay. But in principle now I can do the same thing again, and I know that again here I will the probability if I already know. So this hat A is the information that I already had before. Probability if I already know that I'm smaller than 1/4 here. Probability of actually being bigger than 1/8 in this even a bit smaller interval. Perhaps that should be a 2. No, I think it's right. So on this actually so on this even smaller interval, to be smaller than 1/8, behaves like that. So I have here the prefactor that is a bit smaller, but here in my large deviation bound, I pick up a factor 4 because my temperature has actually changed. Right? And now, okay, let me. Okay.
What's
Yeah.
this x minus 1?
Where's x minus 1?
Yeah, x minus 1, your bound. Ax minus 1.
Oh, no, that's just, okay, I think the x is just completely, yeah, I think it's swapped. The x should really be here. Then it would be better.
K minus 1 times x.
Yeah, k minus 1, the bracket is, so yeah, sorry, the x should be in front of here. Then it makes more sense, I hope. Did I also have that before? I hope not. So it should be this way, right? So that's what it should be. It should look like. Yeah, sorry. Okay, good. So now we iterate this procedure and do it again and again and again. And in the k epsilon step, we have this bound that here. So now if we rescale everything by k epsilon, then we have this this rescaled temperature here, and we have this completely rescaled potential here. And now that's why we can choose the k epsilon to just exactly depend logarithmically on epsilon. So then this becomes an order 1 term. And here this thing actually converges uniformly to just u squared minus 1 times the second derivative of v. And this is important that this converges because I have just told you that we get the bound with the same c. But we really need our large deviation bounds to be uniform in everything. And so that's why we need uniform large deviations again. So we also need our large deviations to be uniform in the v, and that's only true if we have a bound on the Lipschitz function, Lipschitz norm of the potential v. And this, of course, we have this for these kind of rescaled potentials because they converge uniformly. But we really need the uniform convergence in order to have always the same large deviation bound. Okay? But then we put everything together and sum over it, and then we get exactly the bound that we want. Okay? So I have 5 minutes? Okay. So that's nice. So let me perhaps show you another kind of nice argument like that we use on the way. Oh, no, that's what's that? Okay, good. So something that we use all the time, and I have told you that we always have these small extra conditions in our set, and I have completely dropped them. But one of the things we really have to control is the growth of the field for large M. Of course, I mean, this bound doesn't seem surprising at all. The probability that our field, we always think of our field to be between -1 and +1. But if you think about it, we actually, in the proof of the statement that we don't have many transitions, or that the probability, we actually integrate over these large deviation bounds. But these are only uniform if my U potential is actually for U that are contained in a compact box. So we have to have another argument to exclude the fact that to exclude the case that U is very large. So that's what we do in this lemma here. So let me tell you that this is actually not the optimal lemma. The true rate, the true decay rate of U is actually this. So you have a P over 2 plus 1, where if the potential growth of V is just due to the P. So that's the true one. Our argument would perhaps also give you that, but we didn't really care because it didn't matter. Also, let me also point out, this is something I spoke about. Anyway, so this is something that typically people will remark when I write down a statement like that. Of course, the one-point distribution of our measure is very closely related to the ground state of the Schrödinger operator. So, if we were on an infinite domain, then and we were in a stationary case, then our distribution at a given point would be exactly the ground state of the Schrödinger operator squared, I think. But so then this is really exactly a question about the decay of the ground state of the Schrödinger operator. Now, in our slightly non-translation invariant case, this is of course the scaling of the Schrödinger ground function, and this is just something you can get by homogeneity. You can see that. Right, but in a way, so first of all, why we didn't use results from the theory of Schrödinger operators to say that first of all, in our slightly inhomogeneous cases, there's not a very clean way of writing down the relation between the ground state of the Schrödinger and our distribution. And also, if I spend a bit of time looking in the literature of how these results for Schrödinger operators are actually proved, and then what people typically do is they just use actually exactly this representation to prove the decay of the Schrödinger operator. So it seems a bit kind of going in circles, so I thought we could just do it. But so when we decided to just do it right away from here. So let me just give you a kind of a nice picture that should indicate how we prove that. So we prove the probability. We say that we bound the probability of being, say, above 4m. I mean, it doesn't really matter if it's m or 4m. So let's say it's 4m. And then we have two cases. We consider here these stopping points, which is these are hitting points of level 3m. Okay, so they have two cases. Either I go to level 3m very close to 0, or they're actually far away. Right. So these are just the two cases. So so what we do to treat this case where they are close, where they are nearby, we can use this. We can treat this case explicitly by taking large deviation bounds. So that's no problem as long as our interval is bounded here. And here we use another reflection argument. So here in this case we actually reflect our path again, now at the level 2m. And then we can quantify how much potential energy we gain by that. And then this allows us to also exclude this case. I mean, in this case, although of course of course in principle, why would the path want to stay away from plus or minus 1 for very long? It would never do that. But in order to actually exclude it, you can't do this with large deviations because it could potentially be very far away, and your large deviation bounds are only on compact intervals, or at least bounded intervals. Okay, so that's kind of all the arguments that I wanted to show you. Let me perhaps spend a minute on discussing some perhaps alternative developments or some things that we could do from there. So first of all, I mean, I really like the rescaling argument for the close to 1 lemma that I've proved you, but it's actually not the easiest possible argument. So there is for this and also for the one-point distribution lemma, there are simpler arguments that use tricks from statistical mechanics like FKG inequality and Braskamp-Leib inequality, and if you plug them in the right way, you can actually get much easier proofs. But of course, I mean, you have to use these things, and our things are kind of very hand-on. We have now improved our reflection techniques to also cover reflections that almost, well, we have not written anything up, but we think we can. cover cases where we don't have exactly mass preservation, but we can control the errors there. And then we can actually also treat cases where the potential is asymmetric, and it turns out that the phenomena then the behavior seems to be completely different. And also, I mean, in relation to diffusion bridges seems to be interesting. And let me just very briefly summarize what I told you. So we studied the invariant measure of Allen-Cahn in one space dimension, very small noise and large system. We have these matching upper and lower bounds for the probability of extra transitions, where especially we capture these logarithmic, these entropic terms. If the system grows more than logarithmically, the jump is uniformly distributed, and that is sharp. And the key ideas were these large deviation things, these global symmetries, and detailed analysis of the energy landscape. And thanks.
Maybe, I mean, when you're thinking about this one-dimensional case, of course, then the natural question is, how does this large deviation theory for the two-point boundary value problem, right, what it really is, how does it connect to the initial value kind of large deviation theory?
What you mean by initial value is you don't condition on the right point, but you only condition on the left point? Is that what you mean?
Right. I mean, you give for the first derivative, you give whatever is your initial datum. But this, of course, I mean, when you go further away than whatever logarithmic epsilon, and that is already gone. Right? The derivative condition that doesn't you can take any basically. You know. Oh.
True. Yeah.
Because the reason why I'm asking this is because somehow when you see that and in this kind of ODE system which you have there, or let's say second order ODE, there I mean the transitions become become very much different from the transitions which you would have in your in this thing which you were writing down, this discretized version, which was actually a Gibbs measure type of approach, right? Because what is happening is actually that you have a lot of excursions. You have it's like because it's a Hamiltonian system, then what you get is something like how do you call that in English? Like the field do I like the words. Well, maybe I should.
I'm not sure.
Maybe we can postpone to German conversation. And do you have any information when you take because your length should be smaller than the exponential first escape, which is really related to the first time transition time in the finding Wenzel, I think. So if you take this length larger, then you expect more than one.
Oh yeah, then we would expect lots of transitions.
Yes.
Yeah.
So do you have any information for its typical length between two transitions and things like that? This would be the next question, I think.
Yeah, I mean, I think these arguments kind of naturally would allow you to treat this case. So I haven't actually looked exactly at that question, but I mean, of course, you would expect them to be exactly exponential of c naught over epsilon apart, right? So
it would be so larger, even larger, right? So that you have time to see one.
No, I think it would be exactly that. And
maybe the theory by Bouvier to see exactly the precise time of transition would be useful in that case.
I mean, to get prefactors.
Yes.
I mean, the bounds that they obtain in the case for SDEs, of course, look much nicer than these large deviation bounds. But I think to be honest, I don't know.
Okay. The theory works for this kind of equation.
For the invariant measure for these things?
No, but I mean for SPD, it has been.
Right. Yeah, I know there were. I mean, of course, I know these works by Florent Barré and with Anton and Sylvie Melea, and also parallel by Barbara Gens. But I think the question there is a bit different.
Yes, it's a bit different, but it's similar.
Yeah.
Like the time you.
Is that also for degenerate noise?
No, only for this kind of case.
Oh, but in the second order equation would be degenerate noise, right? Isn't it?
I'm talking about this equation.
Well, it's the second order equation.
But I don't
And
understand where the second order.
there's only one noise that is in the system sense that is degenerate.
It's not?
It's degenerate in the system sense.
Yes, of course. But,
Yeah, that's what I'm saying. So it's not the usual thing where you have where you have a noise which is kind of in the whole space for a first order system, right? If you rewrite it as a first order system, it becomes degenerate.
yes, of course. It's,
Is it for that the same thing? There's the Q, right? But there's also the
If you rewrite it as a first order system, if you rewrite it as a first order system, the potential for that system is implicitly given by the transit of the Schrödinger operator, which itself depends on the psi.
Is it really? No, I mean, if you look at these transitions, then I don't know whether it's messy. It's just that the distance function is kind of degenerate, right?
okay. So, other questions? Okay, so we should back again.